Hi all, welcome to today's seminar, which is organized by the EuroCC2 project. The seminar is entitled "A Data Science Pipeline for Big Linked Geospatial Data," and it's given by Professor Manolis Koubarakis, Director of Graduate Studies at the Department of Informatics and Telecommunications at the National and Kapodistrian University of Athens. Let me give a brief introduction of our speaker. Manolis Koubarakis is a professor and director of graduate studies at the National and Kapodistrian University of Athens. He leads the artificial intelligence teams. He holds a Ph.D. in computer science from the National Technical University of Athens, a master's degree in computer science from the University of Toronto, and a diploma in mathematics from the University of Crete. He's a fellow of the European Association for Artificial Intelligence since 2015, and a member of its board since 2022, and previous president of the Hellenic Association for Artificial Intelligence. He's a member of the advisory board that implements the Hellenic National Strategy for Artificial Intelligence, He has published more than 200 papers that have been widely cited in the areas of artificial intelligence, databases, semantic web, knowledge graphs, and linked data, and deep learning for natural language processing. His research has been financially supported with a total amount exceeding 9 million euros by the European Commission, the Hellenic Foundation for Research and Innovation, the Greek General Secretariat for Research and Technology, the European Space Agency, and industry. In this talk, a data science pipeline will be presented that starts with geospatial data in various formats coming from heterogeneous sources and ends with a complete user application. Today's seminar is organized by EuRAI, a pan-European project with more than 30 countries participating. The goal of EuRAI is to enhance the competencies of Europe in advanced technologies like high-performance computing, machine learning, AI, and high-performance data analytics. We offer a series of seminars and training events, as well as customized services for industry, academia, and the public sector. These services include consultation, help with provision of computational resources, or proof of concept projects. So we can give the floor to Professor Koubarakis, and we can start our seminar.
Thank you very much. Is it okay to stand up here, or it's better to go over there for the Okay, thank you very much for the kind introduction. I'm very happy to be here. As you probably noticed already, I have added here Earth observation because we have worked a lot with Earth observation data. But what I will present to you today is essentially what my group has been doing for the last 13 years, I think, on developing a data science pipeline for big linked geospatial and Earth observation data. So I will start by giving the introduction and motivation for what we do. Then I will present the data science pipeline. I'll present some applications that we have developed, and then I will go in depth to present a system that serves a particular stage of this pipeline, and it's a unique in its kind system that we have developed. And then I will present some open questions. Okay, so the reason that we have been doing this work with my group is that there is lots of geospatial data available these days, and it is used by many applications. It's a pity I didn't change these slides to have a map of Cyprus, but I have a map from Hangzhou in China. And there are many apps these days where we can find geospatial data, right? Like Google Maps and OpenStreetMap. And what is important to point out is that there are mapping agencies like the Ordnance Survey in the UK, the Cadastre in the Netherlands, and the Swiss Cadastre Agency that actually offer geospatial data as linked data. I will introduce linked data later and talk about it, but it's important to point out right from the start. And one of the most important sources, possibly the most important sources for applications with societal, economic, and environmental value today is Earth observation data, data from satellites. Which is open and free these days. It started with the Landsat program in the US, and nowadays Copernicus is the flagship Earth observation program that also offer open satellite data. And this data has a lot of impact. There are many applications developed, and it has a lot of financial, a lot of economic impact in various areas of the planet. And many applications, for example, in agriculture, forestry, urban development and cultural heritage, and so on. Climate services, of course, a lot of things to do with climate change, We have been in the nice position to have developed some of these applications that I will talk to you about later. Earth observation in one slide, so you can see where we are working, what we're working on. Earth observation is essentially the science of having a satellite that will capture raw data, send it on the ground segment where it is pre-processed. Then some image processing takes place and raw images are produced and are made available then downstream to companies or universities or other organizations to develop value-added services that are typically offered through a geographic information system. And I will show you how we have actually implemented essentially the same kinds of ideas using semantic technologies in a while. Copernicus is the program of the European Union. We don't need to go into the details, but there are many satellites that send data to the ground segments as I described earlier. And this is really big data. Why is it big data? If you look at this table, data you can get from this website. It's the open access hub of Copernicus. And as you can see here, these are the missions, the various missions, the various satellite missions. You have basically millions of products, millions of these kinds of images that I showed earlier. And if you look here at size, you see, for example, in 2021, there was around 7 petabytes of data. And from the beginning of the program, 32 petabytes. So this is a lot of data. And data constantly arrive in big amounts, in terabytes of data just a month in 2020. And the trend continues. And not only we have this volume and velocity, but we also have variety because typically Earth observation data is processed together with other kinds of data, geospatial data also typically, so that we develop an interesting application, right? We might have various images from different types of sensors. We might put it together with aerial imagery or in situ data. And what's actually interesting to also notice is that if we take this data and process it and extract, let's say land cover classes from it or other interesting information, this information is also big because we are starting from a big data situation. And we are interested also in the veracity and value of this data, but this is not at all the subject of my talk, so I will skip that. The main objective of our work since 2010, when we started working in this area, was to take these silos where typically Earth observation data resides and open them up and make the data available on the web using semantic web technologies, using the data model RDF for representing the data, the ontology language OWL2 for representing the ontology that describes the data, and querying this data using Sparkle, and in that way make this data parts of the linked data cloud that you see here. So what is linked geospatial data? Again, in a few slides. Let's say that we want to model the Greek administrative geography. Again, I apologize, this should have been about Cyprus. But let's say that we want to model the Greek administrative geography using linked data. Typically, what we will do is we will have a domain ontology that says, for example, that in Greece, according to the Kallikratis law, we have the country. Then we have decentralized administrations at the next level. Then we have regions. Then we have regional units, then municipalities, and so on, right? And all of these are subclasses of the class administrative unit. We take such a domain ontology, and because we want to represent geospatial information about the various instances of the classes of this ontology, we have to put this ontology together with a geospatial ontology. So basically what we have done here is we say that administrative geography is a subclass of feature, so that whatever we have later on as an instance of one of these classes, for example, a certain municipality, will end up being a geographic feature as well. Geographers use the word feature not in the sense of machine learning, but basically to talk about an object. So equivalently, we could say object here. And as you see, features have geometries. This is very important because you want to associate geospatial data to it, to a feature. So you get something like this then at the data level. You get, let's say, ancient Olympia. Maybe you want to represent information about ancient Olympia. So you have a feature called Olympia. Its type is municipal community. It has a name. The name is Ancient Olympia. It has a population, which is 184 people. And then it has a geometry also with respect to this cardinal coordinate reference system. And it's a multi-polygon. It's a complex kind of geometry. Okay, so this is essentially the data model. The data model is information about features, and it's in the form of property value, and you can think about this as triples. Like this is the subject of the triple, this is the property, and this is the object. And triples you can represent as directed edges. You have the subject, and then you have the property as the label of the edge, and then you have the object at the end of the triple. And in this way, you can build graphs, right? So it's a graph data model, but you can also see it as an object-oriented data model in this way. So then you can ask queries. You can say, for example, what is the population of ancient Olympia? So this is a Sparkle query. But you can also extend Sparkle to ST Sparkle. This is a language that we have developed that basically offers you more sophisticated geospatial primitives. You can say, for example, that two geometries intersect, or you can union geometries and then compute an intersection and so on. For example, to be able to compute the parts of belt areas that lie in coniferous forests, assuming that you have two data sets, one data set which is about the land cover of areas and a data set that gives you belt areas, okay? These are the kinds of things. So this is, let's say, the SQL of linked geospatial data. And why linked data would be a good technology for us? Because it allows us to unlock open data that reside in silos. It allows us to make this data available on the web using various web technologies. And it allows us, most importantly, to interlink this data with other data, because value comes out of this interlinking. For example, if we have a data set like Corinne land cover that describes the land cover of various areas in Europe, or the Urban Atlas that does the same thing for land cover and land use in cities, then you can have various interesting linkages. For example, for every area for which we know its land cover class, we can see, for example, what points of interest lie in there by interlinking this data with OpenStreetMap points of interest. Or we can see what toponyms, what kind of geographic locations lie in that area, and so on. And in that way, you interlink data and you make it more amenable so that you can develop interesting applications on top of them. So what is the data science pipeline that I wanted to talk to you about? Basically, it essentially copies, let's say, the Earth observation in one slide pipeline that I presented to you earlier, because as you can see, what we are assuming is that we have a satellite that sends us data on the ground where they're ingested, they are processed, images are produced that are cataloged and archived, and then you might get somebody that wants to find a data set of interest, so sends a query to the catalog, okay? And once this data set is discovered, then we might run some machine learning algorithms to extract some kinds of, some interesting kinds of information from that image. So for example, in Greece every summer, we have wildfires, and we might use, as you will see later on in one of the applications that I will show, we might use satellite images to extract hotspots that tells us that there is a fire on the ground, and then monitor the evolution of the fire. Or after the fire finishes, we would like to model the burnt areas that have been produced, and so on. So information will be extracted, and then we transform this information into RDF. We make it essentially linked data then by interlinking with other sources. We can publish it on the web. We have systems for storage and querying. I will present to you one of these systems today. And we also have a very nice system for visualizing these kinds of data, because typically, as you know, I mean, if you have ever seen a geographic information system, a GIS system, everything there is a map, basically, that you would like to show to a user. And this is what we can do with the technologies that we have. So essentially, if you take a look at these two papers that we have written with my team, you will see very briefly what we have done in these green boxes, these stages of the pipeline. We have not worked in these areas at all. We assume that this is made available to us, and then we take over. So our contributions, if I can go through them very quickly, is, for example, for data discovery, we have a question answering engine. So typically, what we can do is we can sit in front of a satellite archive. We can write a question in natural language, and we would get images that satisfy the constraints that we expressed in natural language. So this is a paper we published in IGARS this year. Then we have systems that transform big amounts of geospatial information that might be in shape files into the RDF data model. We have then algorithms for interlinking this data with other data. So this is a system called Geospatial that we will be presenting a version of it at the SIGACT ACM conference in November. Storage and querying, we have been developing systems that are essentially state-of-the-art. I will present to you Strabo 2 today in a while. To be able to benchmark the performance of these systems, we have developed various benchmarks like the Geographica benchmark. And another two areas that we are working very intensely is question answering over geospatial linked data. So assume, for example, that you have a knowledge graph that talks about the administrative geography of Greece, but also information about other geographic features like rivers and lakes and so on. Then we have systems where you can ask a natural language query like what is the river that crosses Larissa, and get a result back. And we have this tool called Sextant for visualizing basically the answers from all of our systems. So what kind of applications have we built? This is probably the application about which I'm most proud of. This is the Fire Hub service of the National Observatory of Athens. In this application, we take images from the severe instrument of Meteosat second generation satellites of EUMETSAT. And from these satellites, we extract hotspots. This is a hotspot that basically tells us that somewhere here near Evia there is a fire, and then we put this information together with information about let's say the administrative areas that are involved, what are the municipalities, for example, in this area, what kinds of critical infrastructure there is in this area, and so on. And the fire brigade has been using this not actively when they fight fires, but usually as an aftermath, as a tool that allows them to see how the fire actually developed according to the system, and judging possibly whether their response also has been the right one. Another application is precision farming that we have done for fertilization of fields. So here we have worked with a German company. Sorry, I forgot to say this earlier. This has been done with the National Observatory of Athens, and actually the Fire Hub service is an operational system at the National Observatory of Athens today, and it actually won a prize also in a Copernicus Masters competition a few years ago. The precision farming application was done with a company with the name Vista from Munich in Germany. And essentially what we have developed is we have developed an application that can run on a tablet, where basically we compile information from satellite images that cover areas where farms are. Through processing, we produce biomass maps, and together with information about plants that it's not shown here, plant models, basically, plant growth models, we can produce fertilization maps for the farmers that have their property on the ground. And we usually put this together with water bodies, protected areas, legal regulations that tell us useful things about where, for example, not to fertilize because there is a specific regulation that tells you maybe not to fertilize, or maybe to fertilize with a specific kind of ingredient. And in that way, we develop a precision farming application that can even run on the tractor. We saw it running on a tractor, and the tractor would then go into the field to do the work. We have developed an application with the European Union Satellite Center that is based in Madrid, these people do geospatial intelligence. So essentially, whenever there is a crisis, like now, for example, in Israel, they will prepare a report for the European Union. And for that, they rely a lot on information from satellites, information from other data sources like social media, but open source, most of them. It's, I mean, if you talk to them, they have amazing stories about what kind of information is out there, essentially, to be picked up with from agencies like this and actually provide them intelligence. You wouldn't believe it. So essentially, in this system, what happens is whenever you see something, for example, in Twitter that they would be interested in, then they look with satellite images in the by using sentinel images, they look at the relevant areas to see what kind of changes they see, and vice versa. When you see changes using satellite images, you would like to see in, let's say, news outlets and also data sources like Twitter to see what is talked about regarding these geographical areas. So this picture looks kind of complicated, but these basically, these two things are the most important things in that application. And another application that I would like to skip about water availability and irrigation that we have done recently. And we have been using also all these things that we have developed in graduate courses in Athens by having data sets that the students can play with. And we have recently written a book also in this area. It's an edited book. I'm the editor, and my group basically has written various chapters where we present basically everything that I showed on this pipeline. Okay, so now I would like to concentrate. I would like to visit this stage of the pipeline where the job is to store and process efficiently linked geospatial data and be able to answer queries efficiently. Okay, so to do this, I will present to you the system Strabo 2. The name Strabo is of a Roman citizen of Greek origin who was a geographer in ancient times. And Strabo 2 is the second version, a parallel and distributed system of an earlier system that we had for Geosparkle query evaluation. Geosparkle is like the language ST-Sparkle that I showed earlier. Geosparkle is an OGC standard. It's very similar to the language that we developed in parallel when the time of this OGC standard development took place. This is a paper that we presented last year at the International Semantic Web Conference, which is the premier conference where we publish similar work together with the web conference. So what was the motivation for developing Strabo 2? The motivation was that current systems like our system Strabon, GraphDB, and Oracle Spatial and Graph, these two are commercial systems, centralized, okay? They had limited scalability with respect to Geosparkle queries. So for example, you could store in them, let's say 100 gigabytes of point data, and then answer efficiently some simple geospatial queries. For example, selections over a rectangular area, okay? The minute that the complexity of the geometries would increase and also the size of the data would increase, the performance was not good at all. At the same time, we had query engines for RDF, no geospatial data though, that were using big data tools and technologies for storing and processing massive RDF data. So what we thought is, why don't we build a system that uses such big data technologies like Spark, Apache Spark, okay? And be able to work with massive geospatial now RDF data sets and be able to answer geospatial queries efficiently. Okay, so in this way we developed Strabo 2. It has a flexible design that allows us to store thematic and spatial data in a database called Hive, so that we get the efficiency of that system. It relies on a query translation mechanism from an older system of ours called on top spatial in order to obtain SQL queries that will run on Hive to give us the results. And we do certain optimizations to get the best of essentially the systems that we have underneath. And through our experimental evaluation, I will show you a glimpse of this evaluation today. We show that the system is scalable, even to very big data sets, taking into account various query characteristics like the spatial and thematic selectivities. And I will also show you that it has better performance than state-of-the-art centralized solutions like the systems, that I mentioned here. Okay, so this is the architecture, the high-level architecture of Strabo 2. So essentially, our system consists of two components, a data loader and a query executor. Everything runs on Hadoop clusters. And right in the middle, we rely on Apache Spark, okay? And essentially, it's SQL system. And for the geospatial data, we rely on Apache Sedona, which is an open source system that can be used basically by Spark to process geospatial data. Okay, so we didn't build anything. We didn't build the system from scratch, like assuming that we have nothing. We chose to rely on existing technology, and as you will see later, we got a lot of efficiency out of that. It's an open question how you build such a system from scratch. We haven't tried it yet. Okay, so let's talk about the data loader first. The data loader takes RDF graphs. Remember, I told you my data model is triples that can be also understood. A collection of triples can be understood as a graph and stores them in the Hive database. Hive is a database appropriate for large amounts of data. It's a NoSQL database. And we do, so we import the RDF graphs in the Hive database. We do dictionary encoding, which means that very big URLs basically are stored in an efficient way by keeping the prefixes somewhere and then encoding and compressing using Parquet the things that you want to store in Hive. We select an appropriate relational schema for storing the thematic and the geospatial data. Thematic is the non-geospatial data, like population, for example, or the name of the country. Geospatial data is the geometries, yeah? So typically vertical partitioning is used here. I will show you what I mean by that in a minute. We have a geometry linking table for the vertical partitioning scheme that allow us to do joins efficiently. And we perform physical partitioning on the columns of the created tables basically using Spark for thematic data and Sedona for the spatial data. So here's an example. Let's say that we have observations. This is from a project that we had very recently, and we worked for, we had an ice monitoring application there, sea ice monitoring. So essentially, you want to monitor ice in the sea, and you have various categories of ice. So the ice that we see here is drift ice. So it's not stuck to anything like an iceberg, for example, or the shore. It flows freely into the sea, and it can be a danger to vessels navigating, let's say, the Arctic. So this is why we want to monitor it. And let's say that we have various observations. Let's say the observations are from vessels nearby, and let's say that we also have satellite images that depict this ice, and this is the data. So you can see here the triples. We have ice 1, which is of type ice observation. It's drift ice, and it has a geometry, which is a point. So it's an observation by somebody. So it's a point. And then we have a satellite image, let's say this one, which also has a geometry. And now the geometry is, of course, a polygon of the satellite image. As I said, this data will be stored in a vertical partitioning fashion. So for every predicate, like type, we have a binary relation, basically, that stores that, and everything goes and is stored in height. Okay, so the same for the company has CT, sorry, for the property has CT, the same for observation geometry, the same for image geometry, the same for as well-known text. And now, by joining basically observation geometry and as well-known text, and image geometry and as well-known text, we built these tables, and we keep the geometries in binary form, and this will speed up query processing quite a bit, because we have pre-computed certain joins and also offer the geometries in binary form, and this is easier to process than during query processing. And the final thing, so this is what the data loader does, but it also, as you might expect, creates indices for the geometries, because the geometries are the things that are the most expensive to be processed. So it creates persistent spatial indices, both in memory and in disk. Now for that, we rely on Apache Spark, but actually it's interfaced with Scala, or rather it's interfaced through Scala, because the Spark SQL interface does not allow us to do this. So this is the code basically that we need to write to set up an appropriate index for the geometry linking table, like a table, sorry, like a table like this one here. Okay. And then the other module is the query translator. Now for the query translation, we rely on a system called OnTop Spatial. What is OnTop Spatial? OnTop Spatial is an ontology-based data access system. This basically means that we have data in various data sources, for example, relational, or for example, web sources, or for example, from Twitter. But we have users that model the data using an ontology, and then they would like to pose a query using that ontology. So essentially what we have is the database administrator creates mappings from the ontology to the data sources, and then you pose a query using Spark, using the ontology terms. This query is rewritten using the mappings. It goes to the data sources, collects the data, joins the data, brings it back to to the user that posed the query. So we realized that we could also use this code, basically, the code base of OnTop Spatial in Strabo 2. OnTop Spatial, by the way, was the first ontology-based data access system that was produced. We had a paper in 2016 with my student Konstantina Beretta on this system. This was Konstantina's Ph.D. Essentially. So we could use OnTop Spatial, but in this case, we don't have a user doing automatically the mappings, let's say, or telling the system what kinds of tables we have in the Hive database. Sorry, we don't have a user constructing the mappings or telling the system what kind of tables we have in the Hive database. This is done automatically. And then during query translation, the spatial operators basically of Geospatial are translated to spatial function and predicates that are supported by Apache Sedona, the system that is underneath, to actually execute basically later on these queries. Because if I can go back, what essentially happens is a query comes, it is parsed, it is translated then into Spark SQL with functions from Sedona. It is optimized by Spark basically, and then runs on Hive to get back the results. And we have interfered in a couple of places to basically make this process more efficient, given the subtleties of and the characteristics of Spark SQL and Sedona. So, for example, if you get a query like find observations of drift ice with geometries that intersect geometries of satellite images, this is the query, and then it is written as a Spark SQL query to be optimized and executed over Hive. And we do two optimizations that are important. The first is to push the evaluation of thematic predicates before spatial joins. One might wonder here, why are you doing optimizations? I mean, just throw this to Spark SQL and they will do optimizations. Unfortunately, they don't. So essentially, we might have the Spark Catalyst optimizer, for example, looking at a predicate like intersects. So how do we intersect two geometries, or rather two tables with geometries, and compute intersection at using the column that contains the geometries? To be able to do that, you have to look at, for example, at what order and what kind of index to use. Unfortunately, the Spark optimizer for the Spark SQL treats functions like this as a black box, so there is no optimization. And if it passes this to Sedona, Sedona might use an algorithm like GSJoin that will be kind of expensive. And for this, to improve the situation, we do the thematic processing first to limit basically the input in the spatial joins, the size of intermediate results, and in that way, we get a better system. So if you have, for example, such a query like the one that we had already before that says, basically, find me observations and images that intersect, then the part like observations of drift ice and images, this is the thematic part, okay? So we create temporary views that actually evaluate these two parts, and then we throw in a query that computes intersects on these views. So we have saved with this selections, we have managed to pass intermediate results that are smaller here, and in this way we gain in efficiency. We also do a trick for spatial selections. So in this case, if you remember, I told you that the data loader used the Sedona Scala RTD interface to partition the data and create indices, okay? So now we want to use these indices. So whenever we have a spatial selection, a spatial filter, we essentially have code that accesses the RDD, stores the result in a temporary table, and then our SQL query runs on this temporary table to give the result. So this was the code, for example, for computing the index. Then if you have a query that says, find ice observations that intersect with this red polygon, then essentially we write code for creating the temporary table temp here, and then instead of relying on the bigger basically table and a table that didn't have indices on it or would have indices on it created by Sedona and then just discarded it, we use the persistent indexes. Sorry, we use the persistent indices that we had here to construct the temporary table, and then we use the temp basically in the final query, and we get more efficiency in this way. Okay, what experiments we have done? Okay, I'm almost done. What experiments we have done? We have experimented with synthetic data. So we have a synthetic workload in our benchmark called Geographica 3, where basically these are hexagons, and they represent, as you can see, the smaller ones represent land ownership. Then we have bigger ones that are states, and even bigger ones that are countries. And we also have lines that might be, let's say, roads, and we also have points of interest that are these dots. And we create, using an ontology that essentially resembles what OpenStreetMap has for these kinds of classes. We create synthetic data. Then we have a data set of 72 queries of all kinds of queries that would be of interest. And then we execute a very intensive workload using this data set, basically 1 terabyte of data. And we measure what we get in terms of execution time for various queries. So it's interesting to see this table of 72 queries and see, for example, how quickly spatial selections go, what do you get, for example, for various predicates, how expensive they are, and then how expensive, for example, are spatial joins, depending on the selectivity of the query, and so on. I give here an average time in seconds, but I think one should learn more by looking at the paper and looking at the details here. We have also examined scalability with respect to dataset size. So here on the x-axis, we have the dataset size, and on the y-axis, we have the execution time in seconds. And the ideal speedup is the green line. And you can see that only in cases, for example, where we have a lot of intermediate results, we get worse than the ideal speedup. In all the other cases, we do very well. And this is scalability with vary now the number of executors in the machines that we use. Here again, the ideal speedup is linear scalability, the green line, and you can also see here that we do very, very well. So it's I mean, you do get the kind of system that you would like to have with Strabo 2. And then, of course, as I promised, I wanted you to show you some results comparing with centralized systems. So we compared, sorry. Back, thank you. So we compared our system with, so this is Strabo 2, and we compared our system with GraphDB, which is a commercial system, and our earlier system Strabon for various data sets, okay? And for 3 kinds of queries. And we can basically show that GraphDB, for example, for spatial joins with, I mean, after 10 million of triples, it basically does not return a result, essentially. Same down here when it's an easier query. After 500 million triples, it doesn't return a result. Strabon, as you can see, our centralized system can return a result, but its time is it's a bit inefficient. And here you can see that Strabo 2 actually wins in most cases, with the exception of, let's say, simple queries where centralized systems would be better, and it's quite efficient if you look at the numbers in seconds. Again, you can see the paper for exactly what the query was and so on. Okay, so this was Strabo 2. What are questions that we are working on at the moment in my group that have to do with Strabo 2, but also with the whole pipeline? I only added some of them. We can discuss with you other open questions later if you are interested in. So the first thing that interests us is how to go beyond Strabo 2. I mean, can we build a system which can store and process the geographic data owned by a national cartographic agency or produced by some satellites of Copernicus? Currently, Strabo is the only system in this area, so we would love to go beyond that in terms of processing extreme volumes of data. Something that we don't do now, although our original Strabon system has a capability to also store geometries that evolve over time. So in that case, spatiotemporal queries are important. We would like to do this in a more scalable way also. And there is a work by colleagues at the University of Piraeus that actually do that. And this is a line of work that we would like to extend as well. A very important area for us is not just query processing, but question answering also. So how do you answer a natural language query, which is spatiotemporal? We have a paper coming up in this area with some colleagues from Germany. Hopefully, it's going to be written up until December, when my student who is working on this graduates. Another system that I would like to advertise is a semantic data cube system that we have developed. Here, the data is stored as a cube, 3 dimensions, yeah, but we still have an ontology in front of it. So imagine, for example, that you have measurements about temperatures, yeah, over time and space, and you would like to know the areas where there is a heat wave. So basically, you would like to model the information using concepts like heat wave, but at the data level have the temperatures, yeah? And then pose a query that says, show me areas that have heat wave, that had heat wave last summer, and when was this? Okay, how do you go from this query, which is a high-level query, to actually returning the information and building a nice map and showing to the user? This is what Plato does together with our visualization system. And we have a nice demo at ACM Geospatial in November. And the last area where we would like to work is how do we develop foundation models for geospatial data? For example, what is the ChatGPT of geodata? Here there is some work recently that is from very big players. For example, NASA and IBM recently made available a foundation model for satellite data, which you can use, for example, to detect fires, to detect floods, to use in environmental applications. ESA recently had 2 calls for projects essentially with the same idea. And there are a couple of vision papers like the one that I cite here that actually have some ideas in this area. This is something that interests us very much. Thank you very much. This is all I wanted to show. To talk about. These are the projects that have funded this work. You can find a lot more in the website of our team, and you can also, if you want, follow us on Twitter to learn about recent things. Thank you.
With the trick that I expect is more.
Okay, let's.
Just press 59.
No, it's a PDF.
Oh, it's PDF. I thought it's hard. So anyway, if you go back and look back, I think we expect that that's 59.
56. Sorry.
So my question was just to understand, comparing, say, the commercial system, which is GraphDB, and Strabo 2, like for the really large data set, it's a huge improvement, right? And I'm trying to understand, like, is there some kind of algorithmic trick that Strabo 2 does that makes creates such a huge difference? Like, at the more, for a non-expert like me, I mean, what is the reason there is such a big improvement compared to the commercial system?
Okay, I will answer the question very, very sincerely. I think the GraphDB people have a lot of pre-existing ideas in their system that they don't want to throw away and build a system based on the most recent technology to deal with this problem. And this is why they are inefficient. Where in our case, so for example, they might use, let's say, Lucene or Elasticsearch to deal with geospatial data. And there, you don't get the indices that we have, they don't have the optimizations that we have, so that's why they don't get the competitive results that we also have. We did the same thing when we built Strabo, which was our first system. We said, what is currently the best technology to do geospatial data? Relational technology, PostGIS. And we want to build something for a different data model, but also has geospatial data. How do we do it? We can do it from scratch, like start from zero, but this is not very reasonable. Okay, so we said, let's put PostGIS in the background, and let's create a system that basically compiles in an efficient way the Sparkle queries, the Geosparkle queries, and sends it to PostGIS to be implemented. So we get the mileage, I think, by assuming appropriate systems as baseline systems and building on top of them, plus our optimizations. But actually, I think anybody could do the optimizations that we have done. It's actually the baseline systems that are good, and this is why we are getting this improvement.
So thank you very much, Manolis. It was very interesting. So just, I'm not expert in the field, but just trying to understand. So primarily, if I say it well, you detect via all these models, you detect things, right? Processes, let's say, whatever. What about the prediction of that? You refer about these spatiotemporal queries. So is it possible to combine, let's say, these algorithms with probably physical modeling or with whatever method to predict what's going to happen in time? For example, you have a fire. To predict the future. I know that's not an easy question, but that's a general.
Well, what I can add to that is that in this case, for example, you would like to have a data model that would support both your data, but also the models, and then write queries on top of them. And there has been some work in that towards this direction by database people, but I haven't been very familiar with what we have done and how far, with what they have done and how far it went. Because it's basically trying to have a more numerical plus data view of your application, and then try to develop, let's say, query processing techniques for that. So your prediction problem could be a query. And there have been works in that area, but I'm not sure how far.
So practically, as a follow-up, let's say, can someone combine this with a simulator like CFD, where someone solves PDAs, combine these queries in order to feed, let's say, the simulator and to predict what's going to happen? Is this something?
If you want to do it in a modular kind of way, this is possible. But I was going a bit far also, thinking how you can do that declaratively, because in databases, that's what we like to do. We like to express what you want, and then somebody optimizes this thing and you get the answer. Modularly, as you propose, it can be done. It's not a problem. Because you're going to put database functionality at the various stages that you need. But I don't know whether you can do it in a sort of a visionary kind of way. I have to look up these kinds of works. I'm not ready to say that they went that far.
So when you're discussing about time there, that's my last point. So how do you see this as a future challenge? Because you refer to time there, temporary. Right.
For us, it's again the same idea. I mean, imagine geometries that change over time, for example. How do you store these kinds of data? How do you query it efficiently? What kind of indices do you have? What kinds of translations would be appropriate, and so on?
So not so much evolution. It's more like
evolution, but after the fact. Yeah. So you monitor the system that evolves, you store the data, and then you would like to make some queries on the historical data.
Thank you.
Good question. At some point, you mentioned about parent area that was southwest of Evia, and you mentioned that in general you have this fire recognition system that the fire brigade uses as an aftermath to see whether they took the fine judgment or not. Is it because it is not accurate enough that they're not using it a priori to determine whether they should take action or not? I mean, is it? I'm wondering. So the question is about the accuracy of the fire recognition system.
It's we are talking. First of all, I'm not sure if they also use it operationally. It's been a while since I haven't kept up with like the exact use of this. But I remember a certain summer they used it after the fires to see what was happening. In actually some situations where there were a lot of complaints that the response of the fire brigade was not the right one and so on, the people from the National Observatory of Athens were telling me that they were using the system to look at the some scenario to see what would have happened if they get back differently. Maybe a problem is the pixel, because the pixel size, as you can also see like from what I showed, is I think something like 15 kilometers by 15 kilometers, 5 kilometers by 5 kilometers, and also so the spatial resolution, because it's a geostationary satellite, is big. Again, I might be giving you some small wrong information here. I have to look it up in the paper, but that was another issue. And the other thing, of course, is that these guys have people on the ground, right? So I think they take most of the decisions that way. Nowadays, that we are also working in another project with the National Observatory of Athens, they are mostly interested in fire and risk monitoring. So this is okay for them, they can use, but now they concentrate on fire risk, because these days, this is what they want. They want to be ready and to have appropriate forces on the ground where they expect a fire to come. So maybe they don't have this problem anymore.
Thank you.
Πρέπει να συνεχίσουμε τη συζήτηση του προβλήματος γιατί συνδυάζω σίγουρα τις μετρήσεις. Το email μου στείλετε το γιατί έχω συνάντηση έχω πάρα πολύ
Ωραία. Να αφήσω την παρουσίασή μου εγώ, δηλαδή να την βάλω στον υπολογιστή.
Όπως θέλεις.
Να την αφήσω για την περίπτωση που την θέλετε.